Hello everyone who is listening my presentation. Here I am Chakraborty and today I am presenting a paper titled on damage detection in 4-point bending test on benchmark RC structure using feature-based fusion. Here is the outline of my presentation. First I will start with the Infrastar Project because this result is part of Infrastar Project, so I will tell something about this project, what is about this project. Then I will come to introduction, methods for damage and change detection, and then I will show the benchmark RC object with 4-point bending test, and then I will show results with conclusion. So what is Infrastar Project? So Infrastar Project is dealing with fatigue in concrete. So in there we have a 3 work package. Work package 1 is dealing with monitoring and oscillation. Work package 2 is dealing with reliability approaches for decision making. Work package 3 is structure and action model. In here there are key figures and 12 ESRs is working in this project, 8 beneficiaries, 3 partner organizations involved in this project, and also there is 1 advisory board. So I'm in work package 1. The leader of this work package 1 is Dr. Niederleitinger, who is from BAM, Germany. And work package 1 is dealing with novel sensors and improve physics-based data processing methods to smarten the structure. The scope of this paper is mainly on this new ultrasonic sensor, which is detailed on ultrasonic wave. And the object I'm considering is reinforced concrete structure, and the method is non-destructive testing, and what we're measuring is the elastic wave velocity changes for load and other effects. In Europe, now most of the structure is over 40 years old, and the incident happened in Italy. Insist us to thinking of safety of the structure. So how the structure can monitor and provide a safety for the people. So structural health monitoring can help in this case. So a structural health monitoring system is the method of translating sensor data into meaningful information about the changes in the structure. So why we need the structural health monitoring? Structural health monitoring actually because if the structure fails, it can cost a lot. Not only cost, but also it can kill lots of people. So what I'm looking for change or damage detection in reinforced concrete using structural health monitoring, mainly focusing on ultrasonic measurement. So what is ultrasonic measurement? Ultrasonic measurement is the active measurements where we need 2 sensors, one for transmit the pulse and another for receiving the response. So to transmit the pulse, we need power amplifier to amplify that pulse so it can travel some distance, and in the receiving end, when it receives that signal, and we need a pre-amplifier because we know that when signal travels some distance, it gets weaker. So to get back the strength, we need this pre-amplifier to amplify that signal, and then we use some acquisition card to acquire that signal and store it in the computer. How these active measurements works? Example in here, so we place 2 sensors in different position. This is the transmitting sensor which is sending the pulse, and in the receiving which receive that response. So if there are no external load or effect in the structure, so the signal remain same. If there is some changes, then the phase of the signal will get changed, and from that we can translate the response of the structure. There are traditional sensors which is available in the market for the ultrasonic measurements, so we can see it in here, and there are different types of these measurements, like direct, indirect, semi-direct, and also indirect. The problem of this traditional sensor is it needs a trained operator to place that sensor in the structure. So therefore, BAM developed the new sensor. You can see the dimension of that sensor in here, which can embed it inside the structure with the river, with this holding cap, so it can measure the response of the concrete. And then actually after we put the concrete, so in this it can remain in the structure. We can see the frequency response of that sensor. So it has a 60 kilohertz in the center frequency and bandwidth of 100 kilohertz, which is good in concrete structure because the wavelength is less than all the aggregate size of the aggregates. In the data acquisition system, we designed a new data acquisition system for this new sensor. And as I told, like we need a power amplifier to amplify the transmit pulse. So we design a power amplifier, and then we design a preamplifier to receive that signal, and also we design the software to control this total measurements. In ultrasonic signal, normally this is the exemplary ultrasonic signal in here. So normally in most of the cases, so the researcher analyzed the first arrival of this signal, but in our case we are considering the diffuse signal, means the total part of the signal which is coming lateral, coming from all over the structure, and this is more informative because it is coming from all over the structure. So we are not considering only direct wave, we are considering also reflective wave. So as I told, like from the ultrasonic signal ultrasonic measurements, we acquire the ultrasonic signal. So to get meaningful information, we have to extract feature. So to extract feature, we have to use some signal processing technique. So in here, we are considering peak-to-peak amplitude to have a features from this raw signal. So we use some window. So as I told, like we are considering the diffuse signal, so we are looking for all part of the signals. So he used the window template, so it can sweep over the signal, and it can see in that way like amplitude changes in each window, and from there we can conclude some response of the structure. And often in the structure we use different kind of sensor like ultrasonic sensor and strain gauges, and they measure actually similar response or similar kind of features. So to get a comprehensive result, we can use some technique to combine this feature and to have one comprehensive feature. So in that case, the CCA algorithm can help us to combine these features. So example, we have a 2-feature matrix in here, and then CCA will look for the correlation between these 2 features, and to get a maximized correlation, so he used the CCA algorithm and to find a pair of projection using this formula. To validate our methodology, we design a beam which is 2.9 meter long and 40 centimeter height, 20 centimeter width. As I told, I'm considering embedded sensors. So in here, before casting, we place the sensor like in the yellow strain gauges, and then red is ultrasonic sensors placed in bottom and top of the sensors. And then also we put 2 river stress meter to measure the stress in the river. In this figure we can see where the sensor is placed and with the red and yellow circle. After that, actually we put the beam with the two support in the stand, supporting stand, and we put the loading machine to do the test, and also so we use the loading we use the loading schedule 1 kilonewton per minute till 100 kilonewton, and then 5 kilonewton per minute to rest of the time. So in here we can see that loading schedule with function of time. So the test was almost 2 hours, and then we can see at the end all the cracks and also the shear failure in the beam. We also use the digital image correlation measurements to locate the strain changes, and also to locate the crack, where the crack was first appear, and also the propagating. So we can see in here at 80 kilonewton we have 7 or 8 cracks, and from the strain changes also we can see the location of the crack, and also with the function of load. In here we put if we put the curve actually from support to support, this is in here to support, and then how the strain changes. So we can see around like 40 kilonewton first the crack appear, and then in other cracks with the function of load. Also, we measured the deflection and crack opening displacement from the DIC measurements. We can see that after 40 kilonewton, the strain was sharply increasing, so which is due to the crack opening, first crack opening in the middle of the beam. And also we can see actually that from the crack opening displacement also at 40 kilonewton it started to sharply changes. Yes. And from ultrasonic measurement we acquired the ultrasonic signals. In here we can see all the signals. So in here we can see till 20 kilonewton in the first arrival it is difficult to tell the changes in the amplitude. After 40 kilonewton we can see some changes in the amplitude, and after 100 kilonewton we can see not only changes in the amplitude but also phase of the signal. And from the result of the strain gauges in the middle, so we choose the middle strain gauges because we are using the fusion technique in the bottom pair of the ultrasonic sensor. So middle of the strain gauges and the bottom pair of sensor, we consider both will acquire the same response from the structure. So you can see after 40 kilonewton in here also the strain is increasing sharply due to crack opening in different side of the structure, and then after 100 kilonewton till failure the crack was again sharply changes. So we can see actually the three phase of the structure from the strain data. We can see from the peak to peak amplitude features, as I mentioned it in my previous slides. So we can see that the peak amplitude was increasing slowly till 37 kilonewton, and then sudden jump when the crack appeared, and then also another big jump in the amplitude. And then we can see the peak to peak amplitude was dropping when the crack because due to crack forming in the structure. And after 100 kilonewton again the changes, it was increasing, as I told in my previous slides that in the time the signal is not changing in amplitude but also phase, so it's increasing in the peak to peak amplitude features. So we saw that actually in peak to peak amplitude and also strain data, so both have a similar response. So if we combine this both data using this CCA algorithm, and we can find actually after 35 kilonewton there is a small increasing in the coefficient, and then the big increasing, yeah, and then it was the coefficient was decreased as crack was forming all over the beam, and then also we can see again it was increasing till failure. And in here also we can see the three phase of the structure, but in here the benefit of this using this feature based fusion, we can see at 30 we can clearly see that at 35 kilonewton the coefficient was increased little bit, and we can observe it in from this figure. Which was not possible from peak to peak amplitude feature. And also the values in fused coefficient, we can see it was not in the negative, but in peak to peak amplitude it goes to negative. So when if someone using the threshold technique to distinguish between undamaged and damaged situation, then it will give us more false alarm ratio. So in this case, when we use the feature based fusion, so it will actually show us it will reduce the false alarm ratio, and it will show us the three stage of the structure. In conclusion, so we'll say I can say that changes in peak to peak amplitude it appears to be a potential and damage sensitive feature for ultrasonic measurements. And then from strain map from DIC shown all the cracks as well as the location of the cracks, and strain map from vibrating strain gauges shown crack detection as well as propagation of crack along failure. And also feature based fusion remarkably shown the three phase of the beam, and also it improved in the sensitivity for damage detection, as we saw it. We can see after 35 kilonewton we can see small changes. And in ultrasonic sensor, it's shown as a valuable sensor for its easy installation and also for its durability. And also we will take into consideration for sensitivity of the proposed feature based fusion in real structure. Thank you for your attention.